Hey everybody, I'm here to talk to you about factors of numbers and algebraic expressions. So if you've ever been confused, you've heard, oh, this is a factor of this number or of this expression, and you're unsure of what that means. Hopefully I can clear some of that up in this video. So I'm going to start just by writing down a number. I'm going to write down the number 24. And what I want to observe is that if I divide 24 by 3, I get 8 with no remainder. And 3 is not the only number I can divide 24 by to get this, right? I can divide by 2 and I end up with 12. Or I can go in the other direction and I can take 24 and divide by 8 and I'd get 3. I can take 24, divide by 12 and get 2. And what this means is all of these numbers are factors of the number 24. I think I missed one. So 24 divided by 4 is equal to 6, and therefore 24 divided by 6 is 4. So all of these are factors of the number 24. So hopefully this helps you understand. And just to say it plainly, if a number evenly divides into another number, then we would say it is a factor of that number. So 3 is a factor of 24. 8 is a factor of 24, etc. So let's do this in a bit more of a rigorous way. So let's take our number 24, and we're going to do what's called prime factorization. So I am going to start by splitting 24 into two numbers that when I multiply those two numbers together, I get 24. So I'll start with 3 and 8. 3 is prime. 3 can't be split up any further. So I'm just going to go ahead. I'm going to choose to circle 3. That's kind of just the notation I use to let myself know, hey, I'm done. And then I'm going to take 8 and I'm going to split 8 into 2 times 4. 2 is prime. That can't be broken down any further. And 4 can be broken down into 2 times 2, which once again, these two things cannot be broken down any further. So we're done. So notice what I have now. I have 24 as a product of a bunch of prime numbers. So I have 3 times 2 times 2 times 2 is equal to 24. And all of these are individual factors of 24. So 3 is a factor of 24, 2 is a factor of 24. But importantly, any combination of those prime factors is also a factor of 24. So for example, 3 times 2 times 2 is 12, which is a factor. 2 times 2 times 2, which is 8, is a factor of 24. If I just wanted to grab 3 or 2, that's a factor of 24. If I wanted to grab 3 times 2, which is 6, that's a factor. If I want to grab 2 times 2, which is 4, that's also a factor. So any combination of these prime factors multiplied together will give me a factor of my overall bigger number. So this is really helpful for us when we have like these big numbers that we're trying to break down into factors. We're trying to factor things out or figure out if we can cancel things, if they're in a fraction or they're being divided. This sort of prime factorization, what we call it, is pretty helpful for these big numbers where we would really like them in smaller bite-sized chunks. I want to kind of expand this idea, though, to not just numbers, but algebraic expressions. So let's recall, just in case we need it, an algebraic expression is going to be something such as this, right? So this is some sort of expression. Notice there's no equal sign that would tell us that it is an equation. So an equation is two expressions set equal to one another. But here we just have an expression. And I'm going to split it up in much the same way. However, now I have this like x and y piece. I have 24 times x times y. I'm going to choose to separate this into a number piece and a variable piece. The number piece, we know what goes on over here. I'll go ahead and just like rewrite. It's 3 times 2 times 2 times 2. We just did that. The X and Y piece it'd just be X times Y, right? And we usually would say that these are prime factors. Now, remember, a variable, it's a number that varies. So we don't actually know if X is prime and if Y is prime. We have no clue. But because they could be prime, we just leave them there. We can't really break them down any further. So 24xy has the prime factorization of 3 times 2 times 2 times 2 times x times y. To go into a little bit more detail, you may have already guessed that if I instead have x squared, I take my x squared, and that can be factored down into x and x. Great. And then the last one is if we were to have something like this. So we have a expression where it is a product of this difference term, this difference binomial. So what I want you to make sure that you understand is that this piece here, you treat it as though it is one single number. You treat it as though it were just like y or 2 or something like that. So if I were trying to factor this down, if I were trying to say, hey, what are the prime factors of this, I would have, once again, I like to split it into the number piece and then the variable piece. And 24, once again, we know how that factors. I'm not going to get into it. We've seen it twice. That's enough. But x minus 3, this cannot be split up into x and negative 3, because remember that this is us trying to factor into two things that would multiply to get the thing above it. So I would actually say a piece like this is prime. So x minus 3 is just prime. Now, if it were squared, then I could say, okay, I got to split this thing up. I've got two of them, right? I've got an x minus 3 and I've got another x minus 3. Apologies for my handwriting. Something along these lines. Okay. So hopefully we have an understanding here of how we would factor down, how we would determine what all of the factors of a single algebraic product to be. So the single expression, that's just a bunch of things multiplied together. How do we split it up into all of its little factors, all of its little parts? Now what we want to do is we want to be able to do a comparison between two different algebraic expressions. So for example, I would like to, well, let's walk it back a little bit. Let's start with numbers first, because numbers are easy. So let's talk about 16 and 24. So I'm just using 24 again. Maybe I shouldn't. I'm going to do a different one. No, we'll keep 24. And I'm going to do prime factorizations for both of these. So 16, I'll say, is 4 times 4. And each 4 can be split up as 2 times 2. 2, 2, 2, 2. All right, great. Those are all prime. I can't go any further. So 16, I can just rewrite it as 2 times 2 times 2 times 2. Cool. 24, I'll show it to you one more time. 8, 2, 4, 2, and 2. Okay, cool. No surprises here. It's still the same thing as it was previously. 3 times 2 times 2 times 2. Okay. Now, what we will often be asked in our algebra or pre-algebra classes is, can we find the greatest common factor of these two numbers? So greatest common factor is exactly what it sounds like. What is the biggest number that fits evenly into both of these? What is the biggest number that divides evenly into 16 and also divides evenly into 24? Well, a prime factorization is very helpful for us. Some of you may already be able to guess what that number is. What is the biggest number that goes into 16 and 24 evenly? If you want to take a moment to guess, maybe pause the video. But I'm going to go ahead and go through the sort of more rigorous way of finding out by using our prime factors. So let's see here. I notice, I'm going to get a different color. Get this green. I'll do the green. So I notice that we have, each of these has at least 3 2s. So they have 3 2s in common. Remember, 3 2s multiplied together is 8. So we know that we have at least 2 times 2 times 2 in common, which is 8. And looking at the other stuff, I see that there is nothing else that the two numbers have in common as far as their prime factors go. All they have in common are those 3 2s. So that tells me then that 8 is the greatest common factor, the biggest thing that fits into both 16 and 24. So that is kind of how we would, and probably on a test, your teacher would insist you show them this way instead of you just guessing. Keep that in mind. Even if you have a good math intuition, your teacher is going to want to see some work, or she's going to make ugly red marks on your paper. So let's go ahead and expand this. Once again, we'll take this concept from numbers, we'll apply it to algebraic expressions overall. So let's say I have 12x squared, and then I have 30xy. And I want to know what the greatest common factor between these two things is. So I'm going to do my sort of method where I take like numbers on one side, variables on the other. I'll kind of split them up. I'll do numbers first. It's just a little easier for me to like break them off and do them one by one. So I get 3, 2, and 2. And then for x squared, that's obviously just x and x. And so I get that 12x squared is this. So I'm going to go ahead and say 2 times 2 times 3 times x times x. So that is my prime factorization of 12x squared. I've split it up into the smallest parts possible. 30xy, similarly, I will put 30 over here. I'll put xy over here. 30, I'll say 10 and 3. And then 10 is 5 and 2, neither of which can be split up anymore. Those are both prime. And then I have x and y here. Okay, so I've got 5, 2, 3, x, y. 5, 2, 3, x, y. All right, cool. Now, similar to the last time, I just want to ask myself, what is it that these two numbers have in common? Which of their prime factors do they share? So I notice that we have 1, 2 in common, 1, 3 in common. I don't have a 5 in common. They both have an x in common. They do not have a y in common. Only one of them has a y. Only one of them has a 5. Only one of them has a second x or a second 2. So it looks like the biggest thing that can fit into both 12x squared and 30xy is 6x. So that is my greatest common factor of these two expressions. All right, let's do just one more example to kind of go through. And let's see here. What would I like to do? I will say 10x, x plus 1. And then I'll say 15 y squared x plus 1. So now once again, we have, yes, this is a sum, but this whole thing, which I'm going to consider to be like one single factor, is being multiplied in with everything else. So like I just have 10 times x plus 1. So whatever number x is, it's one bigger than that. But this is a single number. Okay. Ugh, sorry, my nose itches. Okay, so let's go ahead and split this up. Same as before. So x plus 1. 10 gets split up into 5 and 2. X and x plus 1 gets split up into x and x plus 1. So keep in mind, see what I'm doing here is I'm always treating the x plus 1 as though it's not able to be taken apart. It is one single thing. So I have this piece, I have this piece, I have this piece, and I have this piece. Okay, so 5 times 2 times x plus 1. Oh, dude, I swear. I don't know what's going on in this room, but my nose is driving me nuts. Okay, 15y squared x plus 1. So once again, variables this way, numbers this way. Just keep things nice and organized, nice and easy for me. Got 3 and 5 over here. I've got y squared and x plus 1. And then y squared, I'll just split up into y and y. So I've got 3, 5, y, x plus 1. So 3 times 5 times y times x plus 1. And so I want to look at what's in common between my two different terms. I see that they both contain a 5. I see that they both contain an x plus 1. I should probably do that just to avoid confusion. So they both contain an x plus 1. Ugh. My handwriting could use some serious work. I hope it's legible to all you guys out there. So 5 times x plus 1. Is there anything else? No, I don't see anything else. So it's just 5 times x plus 1 is my GCF. So hopefully this kind of demonstrates to you not just what a factor is. So remember, a factor is something that will go evenly into our bigger whole. So whether that is just a number or an algebraic product, if we can divide our thing evenly into it, then that thing is a factor. And keep in mind that even though it's scary when we add variables, it is just the same rules we use. We just split everything up and we see what we have in common and we put those together. So hopefully that was helpful to you. You guys, I will be seeing you next when we actually take our multiple products together and we try and factor things out. So moving forward in our discussion of factoring overall, I look forward to seeing you there in that next video. Bye.